Good afternoon, everyone, and welcome you all for today's class. Today we will discuss about universal velocity distribution law of the described by the Prandtl, Ludwig Prandtl. Already we have studied about Prandtl's universal mixing length theory, and we have calculated turbulent stresses on the basis of mixing length. Which using that same concept and same equation, we will derive universal velocity distribution equation for the pipe flow in turbulent. This equation is known as universal because it is most appropriate and useful for all kind of calculations that will be followed for all types of the pipe flow. And it is from the concept of mechanics and from the experimental data and modeling, it is a most suitable equation and concept. That's why it is known as a universal velocity distribution equation. It is used for the turbulent flow. So now starting from the before going to describe this equation by using Prandtl mixing length theory, we will discuss what is a hydraulic rough and smooth pipe. How we can differentiate between hydraulically rough pipe and perfectly smooth pipe on the basis of roughness. So that is first we know what is a hydraulically rough pipe and smooth pipe. So topic is universal velocity distribution equation. Universal velocity distribution equation. Universal velocity distribution equation. Velocity distribution equation that we are going to discuss here, and also we will solve one question to make this concept very clear. So first of all, we define what is a rough pipe and smooth pipe. How we differentiate between rough pipe and smooth pipe? So that is based on the concept of take a pipe here. Suppose this is a pipe surface, and these are roughness, because when we see surface microscopically, because pipe is circular, so circumference is a surface. When we see surface by microscope, we see that these are peaks of the roughness. And if we draw a line here, this is a line. This distance measured from the surface is HW, and this distance, this average thickness is measured is epsilon. Epsilon is peak thickness of roughness peaks, maximum thickness of roughness peak. HW means laminar sublayer. If laminar sublayer is above the roughness, then means pipe is smooth. We define that epsilon upon HW if less than 0.25. This ratio, thickness of the roughness peak upon thickness of the width of the laminar sublayer. This is a laminar sublayer. Flow here up to this point, from surface to this point, is a laminar, and above that point it becomes turbulent. So here you find a turbulent core. Above this line, flow becomes turbulent. So up to this point it is laminar, and these peaks are not affecting this flow, because up to this point flow is laminar, and these peaks, roughness has no impact on the laminar flow above this surface up to the height of HW. So if this ratio is 0.25, less than 0.25, then it is a hydraulically smooth pipe. It is hydraulically smooth pipe. If this condition fulfill, it is a hydraulically smooth pipe. And second condition is suppose this surface, and again here, see these are peaks, and peaks are much above. These are peaks, and this is a line. This is a line of laminar sublayer HW, and this one is a epsilon. Epsilon means Width means thickness of the height, you can say height of the roughness peaks is above the laminar layer. So these peaks are above the laminar layer, so these peaks will also contribute turbulence in the flow, because up to this point flow is laminar up to this point only, and peaks are above the laminar layer. So this means that this surface of the pipe is highly rough, because these peaks will also create turbulence in flow. That's why this ratio epsilon upon HW is greater than 50. If this condition fulfilled, epsilon upon HW is greater than 50, then this condition is totally hydraulically rough pipe. It is defined as a hydraulically rough pipe. This is a hydraulically rough pipe. And between these two conditions, there is transition also. If transition fulfills, then 0.25 epsilon upon HW and greater than 50, then transition. If it is transition, sorry, less than, it should be less than. It should be less than, not greater than. It should be less than. If this condition, if this ratio roughness peaks upon laminar sublayer ratio is greater than 0.25 and less than 50, then transitional pipe, neither fully rough nor fully smooth pipe. So between two extreme limits, fully rough and fully smooth, then this is known as a transition pipe. These are condition by which another way we can also define roughness and smooth pipe. So there is another way of defining roughness, and another method we can define it, that is U star and I think U star epsilon upon nu less than 3. Then if this condition, U star is a shear velocity, here U star is a shear velocity and epsilon is a thickness of the roughness, and nu is a kinematic viscosity. If this value is less than 3, then flow is pipe surface is fully smooth, and if U star epsilon upon nu greater than 70, then this is a condition for the totally hydraulically rough pipe. This condition exists for hydraulically rough pipe. U star is a shear velocity. Shear velocity I will define later. Shear velocity, that is equal to tau naught upon rho, and tau naught under root tau naught upon rho, and tau naught is a wall shear stress. Shear stress exists at the wall surface of the pipe. Tau naught is and rho is density of fluid. So this condition exists for the hydraulically smooth pipe, and this condition exists for hydraulically rough pipe, and between these two it becomes a transition pipe, just like we have defined earlier on the basis of ratio of the thickness of the roughness peaks upon the laminar sublayers. This is another way you can define hydraulically smooth pipe or hydraulically rough pipe. Now comes to the main topic, that is universal velocity distribution equation derived by Prandtl mixing length theory. So now coming to describe this topic, we first write what is a Prandtl mixing length equation that we have derived on the basis of Prandtl mixing length theory. So tau t, he defined tau t, turbulent stress is equal to rho Lm square du over dy whole square. That equation was derived by Prandtl himself derived this equation, and we have discussed it in earlier lecture. If tau t means turbulent shear stress. Turbulent shear stress is equal to rho density, Lm is a mixing length, and du by dy is a rate of deformation of the velocity with respect to distance y from the surface. So here let us draw a diagram here. For your reference, this is a pipe, and this is a center line, and this is a circular pipe, and radius of the pipe is r, and we always measure distance r from the center of the pipe, and we take distance y from the surface of the pipe. Always for this you take reference that how we measure different distances. From surface we will take y, and from the center we will take small r, and hole from center to wall distance is radius of the pipe, and here you will get a shear stress tau naught at the surface, that is maximum shear stress. That earlier we have described, that question was like this, maximum shear stress like this. This is maximum shear stress tau naught. And velocity profile, if you draw, velocity profile was like this. This is a velocity profile. Here you find a maximum velocity V maximum at y distance. You will find here at y distance from surface, you will find here velocity u. This is for your reference. Because we take this reference from this pipe to describe equation. So for wall shear stress, we replace tau T equal to tau naught. So for wall shear stress, we replace tau T equal to tau naught, because here is tau naught means at a specific point at the wall, at the surface of the wall. Here we are talking turbulent shear stress means anywhere in the pipe, but when we say tau naught, it means wall shear stress at this is the maximum value. We are talking about the maximum value. Tau naught to wall shear stress, that will be equal to rho, and we also know that Lm proportional to y, and Lm was equal to ky. So replacing Lm equal to ky, so it becomes k square y square du by dy whole square, and taking du by dy, du square equal to tau naught upon rho, and into dy square upon k square y square, taking root here. So du equal to tau naught upon rho under root, and dy by y into 1 upon k. And already we have described under root tau naught upon rho is equal to shear velocity under root tau naught upon rho. This is a shear velocity, and you will calculate this value, you will find a meter per second, shear velocity meter per second. So this is this equation, du equal to tau naught, and taking integration of this equation for indefinite integral, we take integration. So u equal to u star upon k log natural base y plus c. This is equation number 2. So now minimizing this one. So u equal to this equation, u equal to u star upon k log natural base y plus c. This is equation number 2. Here c is a constant. How we find value of constant? So taking boundary condition here. What are boundary condition? At y equal to r. Here from at y equal to r, if you measure it go up y equal to r, then v equal to u become v maximum velocity. U become v maximum. So v maximum equal to u star upon k log natural base r plus c. See here from that equation we can find out constant c. So c equal to v maximum minus u star upon k log r. Putting this value of constant c in equation number 2. So u become u star upon k log y plus v maximum minus u star upon k log r. So you can further simplify this equation. We can further simplify u star upon k log y by r plus v maximum. We can write u equal to maximum v maximum plus u star shear velocity upon constant k log natural base y upon r. If you one another equation, you can say the equation number 3. Now we can convert natural log into 10 base log. That is more convenient too. So what we can do here, and k is value by experimental observation, k is approximately 0.4. Already in Prandtl's mixture length we have discussed that on the basis of experimental observation we have found that k equal to 0.4. So converting 10 base, and here we have to multiply by 2.303. So u equal to v maximum plus 2.303 upon 0.4 and u star log 10 base y upon r. So this equation becomes simply u equal to v maximum plus 5.75 u star log 10 base y by r. This is one of the equation that you can say that is general equation for the universal velocity distribution. Other more convenient form of equation we can derive by using this equation. If it is not dimensionless equation, we can convert this equation into dimensionless number. Dimensionless form. We can derive this equation into dimensionless form. How we can do it? We can derive this equation into dimensionless form. So u minus, what we can do? U minus v maximum upon u star equal to 5.75 log 10 base y by r. So changing sign here, we can write this equation into v maximum minus u. So v maximum, because this is greater than u, v maximum minus u upon u star equal to 5.75 log r by y. This is a most general equation for the universal velocity distribution equation. This is equation number 5. This equation you can easily, because this one is in dimensionless form. This is in dimensionless form and it is more convenient to use this equation for finding out values. Just I want to give one question here so that you can understand. Here v maximum is a maximum velocity at the center line. U is a velocity at any point from the wall or from the center. U star is a shear velocity just very close to the surface, not on the surface, because on the surface velocity becomes 0, but when you see that very close to the surface, this is a shear velocity and you will find some value. That's why purpose that we have defined shear velocity, because practically and theoretically you will find at the wall surface u is 0 by concept of no separation theory, but this is not practical. Practically you will find some value, because you will find some value. That value is a shear velocity. That is a shear velocity, and that basis we will solve one question. Let us solve one question here. Question is that, so that you can understand the concept. Question is, there is a pipe of diameter given. This is diameter given 20 centimeter, and at the center and 5 centimeter from the center. यहाँ पर जो these are velocity 2.5 meter per second and 2 meter per second are given. There is a fresh water is flowing. Fresh water is flowing through pipe. Find out shear velocity and wall shear stress. Find out first shear velocity. That velocity you have to define. Second, find out tau naught, wall shear stress. Question once again, because fresh water density of water is given 1000 kg per meter cube. Question again, please try to understand. This is a pipe of diameter 20 centimeter. Fresh water is flowing through pipe and velocity measured are 2.5 meter per second at the center and 2 meter per second from the 5 centimeter from the center. Either you can measure here or you can measure here. You will find, because velocities are like this symmetrical. Velocity in circumferential. In this point velocity will be same and this point velocity will be same. So at 5 centimeter from the wall, velocity is 2 meter per second. So find out shear velocity and tau naught. So you can use same equation. This equation you can use. V max is a velocity at center, that is 2.5 meter per second. So 2.5 meter per second minus u is given. Velocity at 5 centimeter from the center is 2 meter per second. So 2 and u star we have to calculate equal to 5.75 log 10 base. R is given already 10 centimeter and y is given 5 centimeter. So that is equal to 5.75 log 10 base 2. So u star equal to 0.5 upon 5.75 log 10 base 2, that is equal to 0.289 meter per second. From this equation, you get value to 0.289 meter per second. Now U star, if you know what is the area stress, so put the value this tau naught upon rho under root equal to U star. So tau naught equal to U star whole square into rho, that is equal to 0.289 whole square into 1000. That you will calculate, you get around 83.5 Newton per meter square. This is a way you can solve this equation. So this is the most convenient form of the universal velocity distribution equation, and it is very easy to find values. This is a simple question I have given, but you can solve so many complex questions by using this concept. And thank you very much for watching. And next we will discuss hydraulic jump and hydraulic jump and pressure, hydraulic jump and water hammer, and how we can calculate pressure developed by very fast closing of the valve and very slow closing of the valve. This concept is very, very important, and we have seen that in 2024-25 one question was asked to define water hammer and how to define pressure rise during fast closure of the valve and slow closure of the valve. Thank you very much. I hope you will like this, and I think if you find any doubt in this concept, please make a comment, and you can ask to make video on any topic of the fluid mechanics or other subjects. Thank you very much, and have a nice day.